Welcome to this explainer. Today, we're going to unravel the literal mechanical magic and some pretty impossible math that lets us squeeze these massive data center scale 2026 AI models right onto local machines. And hopefully, without setting your desk on fire. If you've been tracking the explosive growth of frontier models lately, you know the numbers have gotten absolutely wild. So we're going to break down exactly how this compression happens, why the basic rules of the game have completely changed this year, and what it all actually means for your hardware.
Okay, let's just dive right in. Take a look at this number because it completely reframes the entire conversation. 5.6 terabytes. We're talking about Moonshot's 2.8 trillion parameter open weight model, Kimi K3. If you wanted to run this beast natively at FP16, which, by the way, was the standard precision models were trained and shipped at until very recently, it demands an absolutely staggering 5.6 terabytes of memory just to load up. I mean, that is a data center number. It is completely out of reach for practically anyone sitting at a desk.
But here's where it gets crazy. By using the absolute most aggressive, usable quantization we have today, that exact same 2.8 trillion parameter model can be crushed down to just 594 gigabytes. That is a massive, massive reduction. It's essentially taking a towering skyscraper of data and squishing it into this dense, compact block that can actually exist outside of $1 million server farm. And this right here perfectly illustrates the core illusion we're breaking down today. How on earth do you shrink a model by almost 90% without completely breaking its brain? And maybe more importantly, why does even this tiny, quote-unquote tiny, 594 gigabyte version still completely choke a maxed out top-of-the-line Mac Studio? Well, the answers lie in the rapidly evolving science of quantization, and let me tell you, the rules of that science were totally rewritten in 2026. So here's our roadmap for the explainer. First, the impossible shrinking act. Then, the golden math of quantization. Next, the format zoo explained. Then, we'll hit the 2026 paradigm shift, the dynamic quantization magic, and finally, wrap it up with the hardware reality. Let's get to it. Section 2, the golden math of quantization. Let's look at the main fundamental lever that pulls all this weight and makes local inference possible in the first place. Simply put, quantization is not about stripping knowledge out of the AI. Actually, it's about describing each individual weight, well, just a bit more coarsely. Instead of having tens of thousands of possible values for one single number, you map a continuous range onto a much smaller set of discrete levels. Think of it like taking a super high-resolution photograph and turning it into an 8-bit pixel art image. Yes, you sacrifice a tiny bit of fine detail and accuracy, but you drastically reduce the sheer amount of data you have to store in memory and push across your silicon. Which brings us to this golden formula. The required memory in bytes roughly equals the parameter count times the bits divided by 8. It's that simple. So following this math, a 32 billion parameter model running at 8-bit precision needs exactly 32 gigabytes of memory. And that right there perfectly explains why your favorite QN332B daily driver fits so comfortably and runs so effortlessly on a current 64 gigabyte machine. Moving on to Section 3, the format zoo explained. Because honestly, running these models isn't just about raw math. It's about matching the right mathematical file format to your specific physical hardware. What's really fascinating here is how the ecosystem has specialized. GGUF is basically your mixed hardware default. It's the absolute workhorse for Macs, gracefully offloading the work between CPU and GPU. MLX, on the other hand, totally dominates Apple's unified memory, giving you way better tokens per second on something like an M3 Ultra. AWQ and GPTQ are highly calibrated and strictly handle those heavy NVIDIA serving clusters. And then there's MXF4. This is an entirely new beast for 2026. It's a hardware-native, micro-scaling floating point format built directly for Blackwell class GPUs. All right, Section 4, the 2026 paradigm shift. And you know that new hardware-native MXFP4 format we just talked about? That leads us straight into this year's massive plot twist. For years, the drill was totally predictable, right? The big AI labs released massive FP16 models, and we downloaded them and squished them down after the fact. But with models like Kimi K3 natively shipping at 4-bit MXFP4 precision, that era is officially over. The compression that makes local inference possible, it's already been spent before you even hit the download button. The original model itself is already about 1.4 terabytes of heavily optimized weights right out of the gate. So the whole industry has shifted from post-training quantization to quantization-aware training, or CAT. Basically, the model literally learns to be robust to low precision while it's being trained. It gets incredibly good at its native bit depth.
But, and this is a huge but, because there's literally no slack left in the system, it is completely unforgiving if you try to shrink it any further. You just can't casually crush a model down using standard methods anymore and expect it to survive. It just won't work.
Which brings us to Section 5, the dynamic quantization magic. So that raises a massive question for us. If we can't blindly crush these models anymore without breaking them, how in the world did that usable 1-bit 594 gigabyte version of K3 actually get made? The answer is absolutely brilliant. It's called dynamic quantization. Think of it exactly like the load-bearing architecture in a giant skyscraper. Unslough's method pushes the vast bulk of the network down to an extreme 1 or 2 bits, but crucially, it identifies and preserves the really important load-bearing layers, keeping them up at 8-bit. By carefully calibrating this whole structure against a massive 1.56 terabyte lossless reference build, this 1-bit Frankenstein actually maintains a stunning 78.9% top 1 accuracy. Seriously, if you try to do this blindly without calibration, the model's logic would just instantly collapse into gibberish.
Finally, Section 6, the hard hardware reality. Because eventually, all this incredible maths and mixed precision magic hits the cold, hard physical limits of the silicon actually sitting on your desk.
You see, when we look at parameter counts, they actually kind of lie to us. There are 2 major hidden wrinkles here. First is mixture of experts, or MOE. This architecture means you pay the memory penalty to keep all 2.8 trillion parameters loaded into RAM, even though only about 104 billion of them are actually firing for any given word. Second is the KV cache. This is the running memory of your prompt and your conversation. And if you push a 1,000,000 token context, it will secretly eat tens of gigabytes of your VRAM, entirely separate from the model weights themselves. And if you ignore the ultimate golden rule here that your total RAM and VRAM absolutely must fit the quantization size, well, your system starts swapping to disk. And it gets ugly. When someone tried to force K3 onto a 64 gigabyte M1 Max by streaming weights from a 2 terabyte SSD, performance completely tanked to a catastrophic 16 seconds per token. I mean, you could literally brew a coffee between every single word. It is completely unusable. That is the harsh reality of technically loading a model that doesn't actually fit your hardware. So we have to draw a hard line on reality here. Look, a 6-bit Q3 235 billion parameter model, that runs beautifully as a genuine local workhorse on a 512 gigabyte Mac Ultra. But the honest truth at the frontier is different. Running a multi-trillion parameter model like Co3 at its roughly 650 gigabyte combined memory floor, it still firmly demands a 2-machine cluster or an 8-GPU server. The multi-trillion class just hasn't fully reached the single workstation yet. As quantization grows up from a hacky aftermarket trick into this highly calibrated, baked-in feature of the frontier models themselves, the landscape has completely shifted. The big labs are spending the compression before you ever even download the file. So I'm going to leave you with this. With the slack officially gone and the absolute floor for frontier models sitting in the hundreds of gigabytes, is your current setup truly ready for what comes next? Thanks so much for joining me on this explainer, and keep pushing those boundaries.